Hey everyone, we're talking about the units of measurement today and the organizing body that controls the units of measurement that scientists use and lots of organizations use is called the International System of Units, or Système International in French. So that's why everyone calls it SI. And that is a group of scientists who meet to keep the units up to date, and occasionally they change how things are defined. And a very big change happened in 2019. Really big. In the world of units, it's the biggest change that's ever happened. Metrologists the world over were very excited. A metrologist is a person who deals with measuring things and the science of measurement. So before 2019, the units were defined in a way where we still had to depend on a physical object. And at first, a long time ago, all the units depended on physical objects. Like someone found a stick, it was about yay long, they called that a meter, and then everyone called that a meter. And if you wanted to know what a meter was, you went and compared your stick to the official meter stick. You can see that there would be problems with that way of defining units because the physical artifact that is the source could change, and if that happens, then everything has to change. So the SI system slowly moved away one at a time from units that were defined in terms of physical objects. But the last remaining physical object was the kilogram. And until about a year ago, the kilogram was literally a chunk of metal that was kept in a vault in France, and it was kept in a vacuum inside of another vacuum, and it was temperature controlled, and they basically never took it out, except very rarely. And then they had all these other standard masses that were calibrated to be the same as the kilogram, and then if you wanted to go recalibrate your kilogram, you had to literally bring your physical object to France and compare it to theirs. And the problem with that is even then, even with all that careful monitoring, the mass of the kilogram we realized was changing. But if the mass of the thing that is the kilogram changes, then the kilogram changes. And so that's not the best way to define units when you're doing really precise measurements. So the new redefinition is rather complicated, to be honest. And until we understand a lot more physics in IB physics, I won't be able to show you truly how they redefined all of the units. But the idea is kind of simple. They realized that there were these constants of nature that we had measured, like the time that it takes for a cesium atom to undergo a certain decay when it has energy, or the speed of light in a vacuum, or Planck's constant, or the charge of an electron, or Boltzmann's constant, or Avogadro's constant, or this brightness constant. These are all things that we had measured with our current set of units. And they had all of these things had uncertainty. But our units themselves had uncertainty because of the kilogram. So we switched what has uncertainty. Instead of these basic constants of nature having some uncertainty, we said a years-long effort of measuring these as precisely as we could was undertaken, and at the end of that, we set the value of these constants of nature to this. Like on this page, these numbers that you see have no uncertainty. There are no more digits after this, because we're defining these things, like the charge of an electron is now defined as this. So that switches where there is uncertainty. Instead of there being uncertainty on the unit, now there is uncertainty on the old standards. So the old chunk of metal that used to be a kilogram now has some uncertainty because a kilogram is now based on some combination of these constants. I know that may be confusing. until this year, explaining the units was a lot simpler. Now they're a lot more complicated. There's going to be a lot of words on the next few pages that really aren't even, they don't mean anything to you yet, and they may never mean anything as far as IB physics is concerned. But I got all this information straight from the SI brochure. And so this table holds the 7 constants that we chose to define. And everything else, every other unit, can be traced back to some combination of these fundamental constants in nature. So you don't actually need to memorize any of these numbers. We will encounter a few of them when we get to topics that include these, but if you need it, it's going to be in the IB data booklet. Okay, next page. So before 2019, there were what is called base units in the SI system, and people still think of them as base units. They mean less now as base units than they used to, because now everything is defined in terms of those fundamental constants. But you'll still hear me and you'll still hear the IB refer to base units. And the base units were the second, the meter, the kilogram, the ampere, the Kelvin, the mole, and the candela. You can express all of the other SI units as some combination, like multiplying and dividing, some combination of these units. Before 2019, that was the end of the story. Now, you can still express any other SI unit as some combination of these, and we will do that. But really more meaningful is that any unit in the SI system can be expressed as some combination or some formula that uses these fundamental constants. So you can see how we're so close to that change that people are still going to refer to these as the base units, and we're still going to use them as the base units. The official definitions, according to the SI, of the second is it's how long it takes for a cesium-133 atom to undergo a certain transition, and that can be repeated in a lab. And the official definition of the meter is how far light can travel in 1 second. And the official definition of the kilogram is probably the most complicated of all of them now. And so we will revisit. Right now it just says it is defined by taking the fixed numerical value of the Planck constant to be blah when expressed in the unit joule seconds, which is equal to kilogram meter squared per second. So if you know H, there's a formula you can use that will pop out what a kilogram is. That's not a very satisfactory definition, I know, but we really can't understand how the definition. There's a big measuring device that is used to fix Planck's constant, and then you can see how the kilogram has its value. We'll revisit that when we learn about electromagnetism. The ampere is the unit of electric current, how much current is flowing through a wire, or how much charge is flowing past a point in a second. That actually got simpler. Most of the units got more complicated. The ampere got a lot simpler. Now, the ampere, since E, the charge of an electron, is officially defined as this with no uncertainty, the ampere can now just be defined as a certain number of electrons flowing past a point in a second. Okay, next page. The Kelvin measures temperature, and we will learn more about it when we talk about the unit on temperature and heat, but it used to be simpler. Basically, you used to be able to replicate a certain setup of water boiling, and it was called the triple point of water, where there was water and steam and ice all at the same time because you were messing with the pressure and the temperature. that was pretty easy to understand by looking at something and measuring the temperature of something. But now it's defined in terms of the Boltzmann constant, and then there's this equation that we actually will see when we talk about thermodynamics. There's an equation that you can use to get to Kelvin from the Boltzmann constant. And the mole, you might have seen in chemistry, or you're about to see in chemistry. A mole just measures how much stuff there is. It's just like a dozen, except a mole is a lot more than a dozen. The mole got simpler, actually. The mole used to be defined as the number of atoms in 12 grams of carbon-12. But now it just contains exactly Avogadro's number of things. And Avogadro's number is one of those constants in nature that we just pinned down and said, it's this. Here are derived units. So before 2019, there were base units and derived units. And all derived units could be expressed as some combination of base units. You still can do that, but really there's less of a difference now between base and derived units. Really, they're all derived units now because you get to them from those 7 constants of nature. But people are still going to call these derived units, and people are still going to call base units because we're so close to the change. And so anything that's not a second, a meter, a kilogram, a mole, an ampere, or a candela, those are the 7 base units. Anything that's not one of those is a derived unit. So, and there's a bunch of things on here that we may never even see in IB physics, but some of them we will. Like frequency is hertz. You can express that in terms of seconds. Force can be measured with newtons, which are kilograms times meters per second squared. You see how all of these derived units can be written as some combination of the base units. And you don't have to memorize any of these. When we get to them, you'll learn them. Here's a cool graphic that shows that what we used to call the base units, and I'm still going to call these the base units, these lead to all of the other units. And it used to be that the definitions of the base units meant a lot more. And once you fixed all those definitions, everything else kind of took care of itself because they were all combinations of base units. Okay, dimensional analysis. This is probably the most useful part of this lesson. You can treat units in calculations just like they are variables in algebra. And they can combine with each other to form new units, or they can cancel each other out. And by manipulating units in an equation, you can sort of check to see if your work makes any sense or not. And what I mean by that is often we will combine I'm just going to make up some equations. You don't have to have seen them before. Force equals mass times acceleration. Maybe you've seen that one. There's a formula for acceleration that says you can calculate acceleration with v squared minus u squared, all that divided by 2 times what's called displacement, which we'll learn eventually. And if I plug that into there, because that's acceleration, then I'm combining a bunch of stuff, a bunch of variables. And I know none of this makes any sense yet because I haven't defined anything. I know that. I want to show you an equation where you get to a result from combining other equations. And now you may never have encountered this before, but you wonder, does it even make sense? And so you can look at this equation, and the unit of mass is the kilogram. The unit, this is velocity. So there's a meters per second on the top here, and all of it is squared. And then there's you're subtracting meters. That's squared, and then you're dividing by displacement, which has units of meters. The units don't change when you add and subtract things. And in fact, you never add and subtract something that doesn't have the same units. So really, I can just rewrite the top here as meters over seconds, all of it squared. And then I can combine these and try to simplify this expression to see if it equals something that I recognize. And so if I divide what's in here on the parentheses out, that's meters squared per second squared divided by meters. And remember, it's like, that's really over 1. It's really like a fraction division problem. So you flip it and multiply it. And there's still kilograms out here. So this meter will cancel one of those meters, and you're left with kilograms times meters over seconds squared. And you may not recognize this yet, but eventually you will. This equals newtons. And force is measured in newtons. So just by looking at the units, I've verified that this equation could make sense. If these units didn't work out, like if I got something over here that didn't actually equal newtons, then I would immediately know not to even go any further with this equation because the units don't work out. And if the units don't work out, then I must have made a mistake somewhere doing something. So a way to convert units that we're going to use is, it's easiest to just show you an example of a unit conversion and then go from there. So let me write down a few conversion factors. 1 foot is equal to 0.3048 meters. Exactly. And that's pretty good to have memorized. IB Physics is never going to actually require you to have that memorized, but you'll encounter it so much that it's good to just have that memorized. What are some other conversions I could use? Let's say 1 hour is equal to 60 minutes. Hopefully you know that one. 1 minute is equal to 60 seconds. Let's do, you could write 1 meter, or 1 kilometer is equal to 1,000 meters. 1 inch is equal to 2.54 centimeters. So the whole thing behind a conversion factor is, and these are called conversion factors, the thing on the left equals the thing on the right. Keep that in mind. What we want to do with conversion factors is combine them in a way that gets us from the unit we have to the unit we want to be in. So let's say I am converting, let's say at 60 miles per hour. I can write this one up here too. 1 mile is 5,280 feet. Okay, so here's our box of conversion factors. 60 miles per hour is a common speed that you might be going in your car. I want to know what that is in centimeters per second. So there's a lot you have to convert here. You've got to get from miles to centimeters, and you've got to go from hours to seconds. And neither of those conversions has a single conversion factor up here that you can pick. But we can chain together a bunch of conversion factors to get from miles to centimeters. And the way that that looks when you do it the way I want you to do it, which is, this method really will make your life simpler in this class, in chemistry, and in college, I promise. At first, it looks like I'm just overcomplicating things, but I guarantee you, if you get used to doing this, unit conversions will never be a headache for you ever again. So I'm going to multiply by a fraction, and that fraction is going to equal 1. Because if it didn't equal 1, then I'd be changing the measurement. To make sure that this fraction equals 1, I'm going to pick one conversion factor and only put stuff that equals each other on top and bottom. So, for example, I'm going to put 1 mile right here, and I'm going to put 5,280 feet right here. 5,280 feet divided by 1 mile is equal to 1. So I'm not changing the measurement, I'm just converting from one unit to a different unit. And think about these like fractions. The units themselves, I mean. Here's miles, and here's miles. When you have miles on top and miles on bottom, they cancel each other out. Just like if you had a 3 times a 4 and a 10 times a 3, these 3's cancel each other out. So the reason I knew to put miles down here in the first place instead of on the top is that I wanted to cancel out miles and be left with something else. So now I'm one step closer to centimeters, but I'm still in feet. Well, I could go from feet to meters. That's this one up here. So should feet go on top like this? 1 foot, 0.3048 meters. But if I do that, then I'm going to get feet times feet, and I'm going to end up with feet squared, which is definitely not what I wanted. I did not want area. Area has nothing to do with this. So feet should go on the bottom, and then 0.3048 meters goes on the top. Feet cancels out. I'm left with meters. I still want to get to centimeters. I'm in meters, and I know that in 1 meter there is 100 centimeters. So I can multiply by that conversion factor. Now I'm done, but I'm only done with the top unit. I'm done with miles. I'm going to be left with centimeters right here. But I have hours still, and I want it to be seconds. So on the same line of work where I was already working, on the same line of work, just keep multiplying and think about canceling out hours. I know I need to cancel out hours, so hours is going to go on the top up here. 1 hour is 60 minutes. And then hours cancels hours. I'm left with minutes. Well, I don't want minutes, I want seconds. So I know minutes are going to go up here. 1 minute is 60 seconds. Cancel out minutes. Now I'm left with seconds. Centimeters are on the top, seconds are on the bottom. So I've got all the conversion factors I need, and I just have to do math now. The way you do this math is simply take the original number, multiply it by everything on the top. Every number you see in the top of one of these fractions, you multiply. And then every number you see on the bottom, you divide. So I would do 60 times 5,280 times 0.3048 times 100 divided by 60 divided by 60. And you don't have to form some big complicated looking expression with fraction bars and stuff in your calculator. You can really just type it just like this and you'll get the answer. So let me show you what that would look like. With my calculator, I would just do 60 times 5280 times 0.3048 times 100 divided by 60 divided by 60 again, hit enter. And you're guaranteed to get it right, unless you literally type something wrong. 2682 point something, what was it? 0.24. And the units are centimeters per second. Does that make sense? Well, 60 miles an hour is pretty fast. Yeah, you're going to go quite a bit of centimeters in a second. That makes sense to me. That's like 26 meters in a second. Yeah, that makes sense. Another thing you should do in unit conversion problems is ask if the answer seems reasonable. Now, sometimes you'll have units where you don't know if it's reasonable or not, but speeds and distances and times, you can probably decide if it's reasonable. Because if I had gotten 0.0007 centimeters per second, then obviously that's wrong, because 60 miles an hour is fast. I'd be going many multiple centimeters per second, not less than 1 centimeters per second. So if I had flipped some numbers in a calculation somewhere, that might be a good tip-off that you did something wrong. The only other trick with this, so I already showed you, this is a rate problem with a unit on the top and a unit on the bottom. That's already more complicated than if I had just done a single, like I don't know, 1 year. How many seconds is a year? There's only one unit you have to worry about canceling, so put years on the bottom, put 365 days on the top, cancel years. Now put days on the bottom. 1 day is 24 hours. Now days are canceled. Put hours on the bottom so that you cancel this hour. 1 hour is 3,600 seconds. Soon, if you do enough conversion problems, you'll remember this. 60 times 60. And then just multiply out across the top. Because all the things on the bottom, a lot of the numbers on the bottom will often be 1, but they won't always be 1. So remember, if there is a number on the bottom, like up here, you do have to divide by whatever's on the bottom. So this would be 365 times 24 times 3,600. 31,536,000 seconds. So that's a little simpler than the rate problem. And then the only other complication to these conversion problems is if you have a unit that has an exponent, like a power. So, for example, a problem with some exponents in it would be like, let's say I want to convert 10 square feet, or feet squared, to meters squared. Well, it's not very often that you have memorized or can look up easily conversion factors that involve squares and cubes, but I did tell you on the previous page that 1 foot is 0.3048 meters. So if you remember that, that's all you need. You don't need anything else. So start with the measurement you have and multiply by the conversion factor you would use if these squares weren't here at all. So I would multiply by feet on the bottom, meters on the top. But this is not going to cancel. The feet right here don't cancel feet squared. But if I square this whole thing, then that gets squared, or the 1 gets squared, 0.3048, that gets squared, and the meters get squared. Distribute the square to everything. And don't forget to square the number later when you go to calculate the answer. But if feet are squared, then they cancel. And to get this answer, I just do 10 times the number on the top, which is 0.3048, and then don't forget to square it. You will at some point probably, but don't forget. Because when you square it, you actually have to change the numbers too, or you didn't really do anything. And then hit enter, because the 1 on the bottom is just squared. It's not going to do anything. 0.9 something 2929 meters squared. And that you can do that if you were doing like 10 feet squared per seconds cubed. You could just do it as much as you needed to. It doesn't change anything. But those are all the tricks for converting units.